So here's the magnesium in the test tube. Just by tapping a little bit, you can see some bubbles. And so, as always in the landing video, I will go through the entire experiment with the calcium. So let's go ahead and drop about 50 milliliters of water in. So you should not be holding this up in the air. Just set it in your pie pan in case it spills over, but you can see this is quite vigorous. It's actually getting kind of warm. So I'm going to go ahead and set it down. That's putting out a lot of fumes. Okay, so I think the results of this experiment are pretty clear. And in fact, they were probably clear to you even before you started, given the safety measures we insisted you put in place, basically dropping the calcium in a larger volume of water that keeps it cooler, not using a test tube, because if you dump calcium in even a little bit of water in a test tube, it'll spurt right out. So based on these safety measures, you may have foresaw that calcium was going to be more reactive than magnesium. So our results are clear. Of the alkaline earths, calcium is more reactive than magnesium. And if we were to do more metals of both the alkali and the alkaline earths, we would see that sodium and potassium are very, very reactive. And we'd see that of the alkaline earths, strontium would even be more reactive than calcium. I've done these in person, super exciting. I don't recommend you do it. Go ahead, just Google a couple videos, sodium and water, potassium water. It's pretty cool. So there are two interesting things I want to think about based on the results of this lab. The first is this idea of chemical reactivity and how it can be used to identify unknown elements. So if you have a list of elements with a known set of properties, and then you find a new element, or you have a new element that you haven't identified yet, and you test the reactivity of this new element, if, for instance, this new element doesn't react with vinegar, well, just simple logic is this new element that doesn't react with vinegar cannot be any element that's already been identified that reacts with vinegar. So you can roll those elements out. So just more broadly, chemical reactivity can be used to identify metals. The second cool thing I want to bring up based on the results of this lab is this emerging set of data, or a pattern, if you will, that through electrolysis, we've been able to separate out zinc and copper from their respective compounds, but we have not been able to separate out sodium from its respective compound. So when we did electrolysis with a solution of sodium bicarbonate, baking soda, in water, and we out popped hydrogen and oxygen. This was in course 1, the chemistry of atoms. We didn't isolate sodium. We isolated hydrogen at the electrode connected to the negative terminal of the battery. So why didn't we pull out sodium, but we pulled out copper and zinc? So this is a question I posed to you earlier. And now let's just think about this a little bit more. And I'll also throw some other information out at you. If we had a solution of potassium chloride or potassium sulfate or potassium carbonate, if we had a solution of strontium chloride, strontium sulfate, or strontium carbonate, certainly sodium chloride, sodium bicarbonate, which is basically sodium carbonate, or sodium sulfate, these are all solutions that exist from the minerals that they come from. With our 9-volt battery, you would not be able to isolate any of these metals. So you now, or if you existed in the first 2 decades of the 1800s, you would not have been able to discover sodium, potassium, strontium, and even calcium with all those inside of all those compounds: calcium chloride, calcium sulfate, calcium carbonate. So 9-volt batteries would not have enough power to pull out these more reactive elements. So this doesn't answer the question of why we can't pull these more reactive elements out, but I'm just pointing out this interesting, unmistakable pattern that we can isolate these more non-reactive metals, zinc and copper. And if we had like silver chloride or silver carbonate, piece of cake to isolate silver, or certainly gold carbonate or gold chloride, piece of cake to isolate gold. So very non-reactive. So I'm just further underscoring this pattern. Non-reactive metals, easy to isolate. Very reactive metals, very difficult to isolate. And just want to underscore one other point related to this. Not only have we not answered it yet, but it took scientists another 100 years, basically, or 80 or 90 years to figure this little mystery out. So we've been at this a few weeks, so let's give ourselves a little space and time to figure this little mystery out. One other interesting, kind of almost obvious observation to make is that all metals generally, and I've said this before, prefer to react with non-metals over metals themselves. So this is kind of a relationship between chemical properties and physical properties, because all metals share similar physical set of properties. I mean, you can just look at a material and with your own eye kind of determine whether it's metallic or not. So you're observing its sort of physical state. But if you observe its physical state, you can make this chemical statement that that thing that looks like a metal probably doesn't react with the metal. It has this chemical property where it prefers to react with a non-metal. So here's another interesting correlation between chemical properties and physical properties. And I know we're swinging all around in this course because there's kind of so many lingering questions. But again, this is actually how science works. Is there's scientists working on an array of different topics, and only after a while do groups of scientists begin to see connections amongst all this work. So for instance, in chapter 4, let's swing back away from elements into compounds. We'll study some chemical properties of compounds, not chemical properties of elements, and we'll see if we can get any closer, because we haven't really made much headway on this at all, between seeing if there's any intelligent statement we can make that connects the properties of elements to the properties of compounds, because right now we still have this, we still are in this space where the elements that make up compounds are very different than the compounds. So sodium and chlorine, again, are nothing like table salt, which is made up of sodium and chlorine. So let's dive into that in the next chapter.